All right, everyone, welcome to Module 8 of this week. Number doesn't make a whole lot of difference, but we are officially nearing that well-deserved halfway point. But we still have a bunch of exciting topics to kind of get into to continue expanding our automotive knowledge. And this week, nothing less than the gasoline injection system. And we're going to talk about a bunch of different fundamentals related to gasoline injection. This is a big topic in automotive. Why you might ask, and that has to do with a lot of the fuel efficiency factors and the ability to control things. So this module, we're going to talk about some of the main objectives here. We're going to look at the advantages of the direct fuel injection system. We're going to learn about the major systems that are involved, all the little parts that make up the modern gasoline injection system. We're going to compare the system of indirect and direct electronic gasoline system. And then we want to take a look and summarize the operating voltages and levels of other values that are involved with these sensors. In addition, we do want to start learning about the operation of oxygen sensors to control an engine's air-fuel ratio. We're going to talk about what exactly does that mean. And then, of course, all in preparation to get everyone prepared to answer those ASE certification test questions related to the gasoline injection system. So let's get to it. The very first thing that we need to get into is understand what this gasoline injection system is. And we need to know that it uses pressure from an electronic or a mechanical fuel pump, most often than not electronic, to get gasoline directly into into the combustion chambers or indirectly into the intake manifolds. Many of our newer vehicles use electronic style fuel pumps today that can even be variably controlled. And then looking at this image, we can see internally where the spark plug and valves are, and then where the fuel spray is directed, and usually through a fuel rail of some sort that is controlled by an electronic control module. And that fuel is coming from our fuel tank on the vehicle, hence the reason you need to still stop at the gas station to add that gas that we use to move most vehicles around, unless you're driving something that's purely electric. Now, this fuel has a fuel delivery system, and that's going to feed this clean and liquid gas form from that gas tank. So we'll use some kind of fuel delivery system, which would usually be that fuel pump through a fuel filter up to the actual engine. We're going to have an air induction system that we're going to need that filters that air that's coming in. We're going to need oxygen to burn with the gasoline. And then we're going to have a sensor system to determine the pressure and temperature, engine speed, and some of the exhaust cleanliness and so forth for the ECM to make correct decisions. And in order for that ECM to make correct decisions, it's going to need a group of sensors telling it exactly what is going on in the various areas of the engine. That will ultimately determine how the fuel injector is controlled, usually amount of duration that it's open. And that's going to meter a precise amount of fuel that's injected into the engine, taking into account the fuel pressure. And then that controls the amount of fuel that actually gets injected into the engine for the optimal level. So let's start out by learning about the fuel delivery system. How do we get the fuel up to the actual engine? So a fuel delivery system of a direct fuel injection system, sometimes referred to as DEFI, will use an electronic fuel pump or a mechanical fuel pump, and electronic fuel pumps are by far more popular today. It has to go through a fuel filter to clean that fuel, and then there's a pressure regulator that controls the amount of pressure that this fuel makes it up to the engine at. Additionally, we have electronic fuel injectors that are controlling the fuel flow to it, and then we have the connecting fuel lines that are involved with this system, simply to get the fuel up front. Then we got to take into account atmospheric pressure and vacuum. And atmospheric pressure is formed by the air surrounding us. At sea level, this is 14.7, and we need to adapt to that air pressure density at higher altitudes as the vehicle moves away from the ocean level. That lowers the amount of fuel that must be injected into the engine as we have higher altitudes because we have less oxygen. And then, of course, we got to deal with the vacuum side of this. That's going to also change as we move this vehicle up into those areas. This vacuum pressure also changes as the vehicle moves. So many of the sealed parts that are in the engine contain vacuum pressure or lack of pressure. And this is measured in various parts of the engine. These differences in pressure are what actually cause some of the flow changes. So the engine uses the difference in pressure, atmospheric pressure, to actually help to force air into those cylinders, right? We're also using vacuum inside those combustion chambers on a certain stroke to actually draw in this fuel and air mixture. So we're using vacuum in this case. The engine actually acts as a big vacuum pump that's constantly bringing in air and pushing it out. And this low pressure area is produced in the intake manifold. So always think when we're using a vacuum gauge, we're usually hooked up to something around the intake manifold area. And that's what pulls air into the engine to support combustion. Taking a look at the engine throttle valve, this is the butterfly or a flap style unit that's in the valve body itself. And that controls the airflow, which inadvertently is going to transfer to engine power output. As that throttle plate moves, we adjust the amount of air that's going in. We'll also adjust the amount of fuel being injected into the combustion chamber. The accelerator is connected to the throttle valve that's actually in the throttle body. Now, a little tip to know about is that in today's gasoline direct injection engines, the engine speed can be controlled without a throttle valve. So there's a little bit of a variation there because now we can actually control electronically those injectors just by moving the accelerator plate, or the accelerator pedal, I'm sorry. The fuel injection quantity and the timing can make that engine idle. And then for safety measures, manufacturers use throttle valves to protect against engine runaway if an injector starts to leak or an ECM were to fail. So when we're looking at this throttle valve, when the accelerator pedal is pressed, the throttle valve opens. Now what's really important is to know that the outside pressure is much higher than that being sucked in by the pistons going up and down. That creates this low vacuum in that area when the valve is opened up. So in other words, the pressure outside is going to equalize that is after the throttle plate. So just think about this because we're going to learn about ported vacuums as we get deeper into automotive learning. Here we can see when the throttle valve is closed. Now the atmospheric pressure outside will typically stay around the same amount, but it can't rush into the intake manifold. And you'll notice that now there's what they call an absent or low pressure inside that intake manifold, which creates a high vacuum. That's obviously when that throttle plate is closed and the engine will return to idle at this point, or this is very near where that throttle plate would set it idle, usually when in park or neutral. One additional note to know is that with diesel engines, we don't use throttle valves on them. They remove the throttle valve and the throttle body from the intake track of the engine, which reduces the pumping losses and improves diesel engine efficiency. They literally use a direct injected rack. It's called a fuel rack that actually moves, that controls the amount of fuel, and obviously adding more fuel, more combustion wants to occur and more air will naturally rush in. Now, an important term to know in our business is this throttle by wire, or sometimes called drive by wire. This is where they have removed the cable from the accelerator pedal inside the vehicle and used an electronic type of potentiometer or Hall effect sensor, and it mimics where the accelerator pedal is. It electronically sends a signal that actually makes the throttle plate move, and that in turn lets the ECM know that information. Here we can see the two components for this throttle by wire or drive by wire system. We'll have an accelerator pedal, what they call a position sensor on that accelerator pedal that will send an electronic signal to the ECM, and the ECM in turn will send a signal to the throttle valve, and the throttle valve has a servo motor that will adjust that throttle plate to mimic the accelerator pedal being requested by the driver. So the servo motor that's part of this throttle valve on the drive-by-wire system is a small reversible servo motor, and it's got a built-in emergency release. We'll talk about that in a second. But the first part to understand is that the ECM will send current through that actuator in one direction to make it open. It will reverse polarity, and it will make the throttle valve close in the opposite direction. Now, of course, there's a bunch of redundancies built into this with checks between the ECM and the throttle valve, but there are some built-in throttle safety release mechanisms, and that throttle safety release will return the engine to idle if the engine throttle valve actuator was to fail. It has an electronic clutch release mechanism in it that disengages the engine throttle actuator if the ECM detects a problem. Usually this is done under the spring tension, just returns it back to closed. So gasoline injection timing becomes a pretty important topic. Now on older vehicles, we had what they call continuous. The injector sprayed fuel whenever the engine was running. And then later on it became intermittent because there was waste here with this gas evaporating before it was actually being burned, and also running very rich systems. We needed more control, and the intermittent injectors closed into this. Today we use timed injection that sprays fuel during the intake and compression strokes related to the piston and valve action. So the amount of time, or what's called injector pulse width, is the amount of time each injector is actually energized and kept open. The longer it's open, the more fuel that can be allowed to pass by it to enter. The ECM takes in sensor readings for the critical engine operating conditions, and we'll talk about those sensors. And then the injector from those sensors is controlled by the ECM based on either a shorter or longer pulse width to either richen or lean that fuel mixture out. Now, when we look at direct and indirect, when comparing the two, direct injection system sprays high-pressure fuel into the engine combustion chambers. And this is usually very high pressure because it's got to overcome the pressure inside that chamber. In indirect injection system, this is where it sprays the fuel into the engine intake manifold, usually very close to the intake valve. These don't have to be quite as high of a pressure, and were very popular for a long period of time. So here on the direct fuel injection systems, you can see that injector dead in the middle. And that injects fuel directly into the engine combustion chamber. And this is where we get that term direct electronic fuel injection, DEFI. And these have an electronic fuel pump, and then they have a mechanical fuel pump. The electronic fuel pump is usually referred to as the low pressure pump, where the mechanical creates the high pressure, usually run by a camshaft in many cases. Now, with the direct fuel injection, we have two types of charge modes. We have what they call a stratified and then a full power charge or homogeneous setup. In the stratified mode, we're using light, ultra lean amounts of fuel that are being added into the combustion chamber. And in the full power charge mode, this is where we can actually add larger amounts of fuel and actually do it up to 3, 4, 5 pulses a combustion stroke if needed. With the counterpart indirect injection systems or multi-port injection systems, there's fuel injectors in the cylinder head intake ports. Remember, these are the ones that sit right behind usually the intake valve, but are in the actual intake manifold. And then there's air fuel runners or passages going to each cylinder. These are called swirl flaps sometimes to really mix up this fuel. And there's usually one injector for each engine cylinder. The types of injectors that are physically used in each of these systems is different. The solenoid fuel injectors have an electronic current that's energized and pulls this electromagnet that pulls the fuel valve open. And that's used with the port and some of the direct fuel injection systems. The Piezo style fuel injectors are used only in direct gasoline, and diesel injectors are very special and can be a bit fragile. Internally, looking at the solenoid style fuel injector, the components, you have the electrical terminals that actually the computer controls the up and down pulsing of these. There's an injector solenoid in there. There's a small inlet screen to prevent any small particles from getting in there. Preferably, we haven't seen that because it's been filtered out by the fuel filter. There's a needle valve and a seat with a return spring and O-ring, and then of course the injector nozzle. Now, if we look at the solenoid fuel injectors, you'll see that there's a control module that energizes the injector. It's usually ground side controlled. This, when current's allowed to flow through it, creates this magnetic field that causes the solenoid to pull up away from the pintle and actually allow fuel to flow. And when it's switched off or the ground is removed under spring pressure, this solenoid valve, the injector, will close. Now, the Piezo fuel injectors, they use a crystalline ceramic material instead of an electromagnet, to open the fuel injector. The electrical energy is converted directly into motion, and these are more precisely able to actually meter the fuel that's passing by those cylinders. These Piezo crystals, you'll learn more about them. We use them in different systems within the vehicle. Now, the fuel pressure regulation on these, there is again a fuel pressure regulator, right, that controls the amount of fuel pressure that is in what they call the rail, and the rail connects to the top of each injector. The direct electronic fuel injection fuel pressure regulator uses an electronic solenoid to bypass excess fuel pressure back to the low pressure side of the system. This has been common for many years with our fuel systems. Now, on the electronic fuel injection fuel pressure regulation, the engine vacuum often would control the fuel pressure in the multi-port fuel injection systems. So as you might recall, vacuum in the system is very high when it is at idle, and it drops when you open the accelerator, and this spring tension that is in the regulator would respond to that vacuum change and either increase or decrease fuel pressure. With direct electronic fuel injection, the pressure regulator is found to be what they call normally open. And that means that if there's a loss of electric power to or from the ECM or an injector, if there's a failure, it'll reduce fuel pressure. And that prevents some failure from occurring that would generate excessively high fuel pressures that can be very dangerous. Most of these systems will actually block the inlet to the pump to stop all mechanical fuel pressure, which really increases that pressure. Now, the fuel rail that's found is usually a large diameter steel tube that's capped off at both ends, and then the only outlets are what are connected to the fuel injectors. That large diameter tube feeds the gasoline to the inlet fittings of those fuel injectors, and the fuel system usually will have some kind of service fitting on it. That service fitting is used for the low pressure side of the EFI systems for releasing and measuring fuel pressure. Now, the direct electronic fuel injector has an amplifier, and an amplifier does exactly that. It increases the voltage and current signals sent from the ECM to operate those high pressure direct injectors. These can be up to 100 volts DC that are required for proper solenoid operation. You can check the operating voltages for injectors in service information before connecting your test instruments to prevent damage. The fuel control sensors that we need to be most aware of are listed here. And you'll see everything here from oxygen sensors to mass airflow sensors. All of these sensors listed here have some kind of effect on the engine and are providing information to the ECM so that the ECM can properly identify the correct amount of duration if it's a solenoid injector, or again the time on a direct electronic fuel injector. These sensors right here are the ones that we're probably most familiar with if you've been in the automotive field, because these are the ones that often fail and cause that dreaded check engine light to illuminate. Any one of these having any type of failure, and not just a complete failure, the ECMs are actually very smart and they're looking for deviations that are considered irrational, which again would trigger a check engine light. And again, here are even more of those common sensors that are taken into account for fuel control. And, this list continues to grow as we want to make more and more precise measurements of the fuel system. So you will notice if you go back on vehicles, they may start out with a few sensors for that input compared to today's vehicles that have many of these sensors involved in that fuel determination. Okay, so next up on our sensors is this oxygen sensor. I'm sure many of you have heard of at some point, or an O2 sensor. And this sensor is in the exhaust gas, and it's called an oxygen sensor because it's doing that. It's measuring the oxygen content in the exhaust gas to check that combustion efficiency. Now, this is what they call a zirconium dioxide style sensor. You can tell that because it operates between 0.1 and 0.9 volts based on the oxygen content in that system. You'll also hear about air-fuel ratio sensors, different style of sensor that perform a very similar function. Now, with these oxygen sensors, we often have multiple oxygen sensors, and they're serving as one being the primary oxygen or O2 sensor, and that monitors the oxygen in the exhaust gas that leaves the engine. The secondary oxygen sensor, or rear O2, is mounted downstream in the exhaust system, usually after the catalytic converter. This catalyst is primarily what's being monitored by that second O2, and it's like it's saying here, it's actually located afterward. This controls some of our what they call fuel adaptations or long-term fuel adaptations that we'll discuss later in your engine performance classes. So here you can see that the front O2 sensor and the rear O2 sensor, the signals that are going on are, or should be in many cases, are have this up and down swing. Now, we don't typically want to see these swinging together, so of course we need to make sure that the catalyst is working correctly. And again, in your engine performance classes, we actually use these sensors to help us identify some catalyst failures. Now, the number of oxygen sensors are assigned by location and in order to the relation of the number of engine banks. In other words, a V8 would have 2 engine banks, a V6 would have 2 engine banks, but a 4-cylinder typically would be an inline 4-cylinder. They make an inline 6-cylinder and an inline 8-cylinder. But the sensor closest to the number 1 cylinder is denoted as oxygen sensor bank 1, sensor 1. And this is true for almost every manufacturer out there. With these, after these O2 sensors, we often hear this term open loop and closed loop. So open loop is when the electronic fuel injection system does not use engine gas content as a main indicator of this air-fuel mixture. And closed loop is when it indeed is using information from oxygen sensors and the other various sensors. In other words, when the engine's first started up cold, it has a pre-mapped ability to use a certain fuel and air ratio until the engine warms up, till those sensors get up to a certain operating temperature, and then actually fuel control takes over at that point. Now, O2 sensors have some other variations that are out there. There's what they call narrowband oxygen sensors, and those only measure combustion efficiency at what they call a near stoichiometric ratio. You'll learn about this, but this is usually this 14.7 to 1 number. Then there's what they call zirconia oxygen sensors, and they use a zirconia and platinum to produce a voltage output that represents oxygen in the exhaust. Those are the ones we were just mentioning a bit. And then there's what I call planar sensors. We'll get into more detail about how these sensors work later on, but understand that these are used to identify lean burn fuel mixtures, measures oxygen content in that exhaust system of a lean burn engine. And then those titanium oxygen sensors, they use a thick film of titanium to detect oxygen present in the exhaust system. It varies its internal resistance. It's a little bit different. It's not a voltage generator necessarily in this case. Wideband O2 sensors are probably the latest and greatest technology that's out there. Those change output gradually and in direct proportion to the oxygen content of the exhaust gases, so they're far more accurate. They produce a small O2 sensor pump current that represents oxygen content in the vehicle. So these aren't measured the same way, and we have to use some different strategies with these. The next sensor we'll discuss here is the manifold absolute pressure sensor. That measures pressure or lack of pressure, known as vacuum, inside the intake manifold. And that varies the resistance with changes in engine load. So as that throttle valve opens up, as we mentioned earlier, the vacuum or pressure inside that intake manifold is going to change. And that data is used by the computer, the ECM, to alter that fuel mixture based on its knowledge of the outside pressure. There are other fuel sensors that are involved. The throttle position sensor, very commonly used, was a variable resistor connected to a throttle plate shaft, and you got different current levels out of it based on its position. And then there was the engine coolant temperature sensor, a very important sensor that monitors the operating temperature of the engine. When the engine warms, the sensor resistance changes, and the ECM then knows to make the fuel mixture leaner. Some other of these sensors, the airflow sensor is used on some of the electronic fuel injection systems to measure the amount of outside air entering. The most common version of this is the mass airflow sensor that's used on many vehicles. There's also an intake air temperature sensor, and that measures the temperature of the air coming into the engine. Another very critical sensor, the crankshaft position sensor, sometimes known as the CPS, that's used to detect engine speed as well as misfire in many cases. We also have fuel pressure and fuel temperature sensors. The fuel pressure sensor is mounted on that rail, and it sends an electronic signal proportional to the pressure inside the rail to the ECM. We also have the fuel temperature sensor, and that monitors the temperature of the fuel in the fuel rail. And that may all be housed in one unit in many cases. As these sensors are upgraded, they get combined together into one unit. Some of the other sensors that also affect data about operating conditions and the engine's fuel need, the AC compressor sensor, telling the engine when the AC compressor is engaging. Some of our transmission sensors, when the actual transmission's in a shift. EGR sensor, right, our exhaust gas recirculation sensor, letting it know when we're using inert gas. There's also the engine knock sensor, which will determine if we're pinging, right, and detonating. There's also the idle air control motor that helps control engine idle speed on some vehicles. This is a solenoid or a servo motor operated that creates this air bypass. The ECM opens the air idle control valve when temperature sensor signals are indicating it's a cold engine. That increases the idle speed to keep the engine from stalling. And as the engine warms, the ECM gradually closes the valve, reduces engine speed to curb idle or normal RPM. Now, again, if you guys have any additional questions related to this, please feel free to send me an email. I'm always just an email away and more than willing to try to go over any of these topics that you have further questions about. Okay, thanks again for watching, guys, and we'll see you next week.